Ionic mobility. Although at infinite dilution, all electrolytes are completely dissociated, their molar conductance differ vastly from one another. This is due to the difference in speeds of the ions. For example, if you consider the molar conductance at infinite dilution of HCl, its value is 379 Siemens centimeter square mole raised to minus 1. Whereas if you consider the lambda 0 value of NaCl, its value is only 130 Siemens centimeter square mole raised to minus 1. So it can be seen the molar conductance at infinite dilution of HCl is almost 3 times that of NaCl. And both these electrolytes contain common anion. This means that the speed of H plus ions is almost 3 times that of Na plus ions. So different ions move with different speeds, and the speed of a particular ion depends upon the potential applied. And if you keep the potential applied constant, then the speed with which an ion moves will be a constant, and that value is known as ionic mobility. So ionic mobility is defined as the distance traveled by an ion per second, that is the velocity of the ion under potential gradient of 1 volt per meter. So under unit potential gradient, and potential gradient means it's the potential difference applied at the electrodes divided by the distance between the electrodes. And mathematically, ionic mobility can be expressed as speed of the ion divided by potential gradient. And its unit, so here meter per second, that divided by volt per meter. So the unit of ionic mobility is meter square volt raised to minus 1 second raised to minus 1 in SI unit. So for a given ion, the ionic mobility is a constant for a given temperature, and the ionic mobility usually ranges in the order of 10 raised to minus 8 meter second raised to minus 1, and this value is extremely small as compared to the speed of gaseous molecules. That means the mobility of ions is small compared to the speed of gaseous molecules, and the low mobility of ions is attributed to their small mean free path. This is because the ions during their movement they undergo frequent collisions, so the mean free path is small. Now let us see how to determine the ionic mobility. So the direct determination of ionic mobility of a specific ion is based on the movement of a visible boundary between two electrolyte solutions. So if you want to find the ionic mobility of K plus ions, an electrolyte containing K plus is taken as the principal electrolyte, for example KCl. And another electrolyte that is known as indicator electrolyte is chosen in such a way that it should satisfy the following conditions. One is it should have the same anion as that of the principal electrolyte. So here the anion is Cl minus, so an electrolyte containing Cl minus ions. Then one more condition, the mobility of the cation should be lower than that of K plus ions. So an electrolyte is chosen in such a way that the anion should be common, then the mobility of the cation should be lower or slow. The cation should move slower compared to the K plus ions. And the experimental setup is shown in this figure. Here KCl is the principal electrolyte, and CdCl2, cadmium chloride, that satisfy both conditions because it contains Cl minus ions and it contains Cd2 plus ions, which is slower compared to K plus ions. So this is a glass tube of uniform bore. Cadmium chloride is taken, then KCl is taken above it, and since cadmium chloride is denser compared to KCl, KCl floats on cadmium chloride, and you can see distinct separation between the two electrolyte solution, and this is the boundary between the two electrolyte solutions. And when an external source of EMF is applied, what happens is K plus ions move towards the cathode and Cl minus will move towards the anode, and along with K plus ion, the slow moving cadmium ions will also migrate towards the cathode. And after some time, you can see the boundary moves upwards. And if you measure the distance moved by the boundary, and if you know the applied EMF, you can calculate the ionic mobility. So here, when current external source of EMF is applied, the boundary remains sharp and will move gradually upward, and its movement being determined by the rate of movement of K plus ions, because K plus migrates at a much faster rate compared to Cd2 plus ions. And if the boundary moves by a distance, say x centimeter in t seconds, and if the potential applied is E volts per meter, then the mobility of K plus, that is given by the expression speed of the ion divided by potential gradient, and that equals x by t divided by potential gradient E. Now, what is the relationship between ion conductivity and viscosity? So, if you consider an ion with a charge number Z in solution that is subjected to an external electric field E, it is accelerated by the electrical force, and that is given by the expression Z E into E, where E is the applied EMF, E is the electronic charge, and Z the charge number. And this moving ion will be retarded by the frictional force due to the viscosity of the liquid, and the frictional force is given by the expression 6 pi eta R into V. That is Stokes' law, where eta is the coefficient of viscosity, R is the radius of the ion, and V is the velocity of the ion. And this ion will be balanced by these two forces. So we can write Z E into E, that equals 6 pi eta R into V. Or we have V by E, that is speed of the ion divided by the EMF, and that is same as the ionic mobility. Ionic mobility. And that equals Z E divided by 6 pi eta into R. And the ion conductivity lambda plus or minus ion equivalent conductance or molar conductance, that is given by the expression U plus or minus into Z into F. Or we can write this expression as lambda plus or minus that equals U is Zd divided by 6 pi eta R. So that into Z into F, or molar ionic conductivity that equals Z square into E F divided by 6 pi eta into R. For a given ion, you know, the value of R and Z are constant, or you can write this expression as lambda plus or minus into eta is a constant, and this is known as Walden's rule. So for a given ion in different solvents, the product of molar ion conductivity and the coefficient of viscosity of the liquid is a constant at given temperature. Or at infinite dilution, you can write this expression as coefficient of viscosity into lambda plus or minus 0 at infinite dilution, that's a constant. And one of the limitation of Walden's rule is, this rule is generally obeyed by larger ions such as tetramethyl ammonium ion, picrate ion, etc. And it is but not by smaller ions. Reason is, in the case of larger ions, they are less solvated, so their effective radius is almost same as their crystallographic radius in different solvents. Whereas in the case of smaller ions, they are highly solvated and their effective radius is larger than their crystallographic radius and is different in different solvents. So Walden's rule, that is product of coefficient of viscosity and molar conductance, is a constant that is obeyed by larger ions.